Good afternoon and welcome to today's Machine Design EHS Today and NED webinar titled Engineering Safety Control Measures, presented by Endeavor Business Media and sponsored by Schmersel. Schmersel is a safety industry leader with 80 years experience in the design and manufacture of machine safety products, industrial switches, position sensors, and control accessories for a wide variety of applications, focusing on ways to protect machinery operators and maintenance personnel from recognized hazards without compromising productivity. I'm Rihanna Beg, Editor-in-Chief of Machine Design with Endeavor Business Media. To begin, let me explain how you can participate in today's presentation. First, if you have any technical difficulties during today's session, please submit to the questions window and our technical experts will help you out. We recommend disabling any pop-up blocking software or extensions in your browser, as these can cause issues with the webinar player. Also, we welcome your questions during today's event. We will answer as many questions as possible during the Q&A session that will follow the main presentation. But please feel free to send in your questions at any time. To do so, simply type your questions into the question window on the side of your screen and hit the submit button. To refer a colleague to today's discussion, share it on social media, or access event resources, click the icons on the left side rail of your screen. And also be aware that today's session is being recorded and will be available on Machine Design, on EHS Today and NED websites within the next 24 hours. You'll be notified by email when the archive is available. Now let's meet our presenter. It is my pleasure to introduce Devin Murray, Technicum Services Manager with Schmersel, I'll say that, Schmersel USA. Devin has amassed more than 15 years of experience in machine safety. He is a TÜV certified functional safety engineer and functional safety trainer who has developed training programs, conducted risk assessments, and authored white papers on machine safety. He holds a Bachelor of Science in Electrical Engineering and an MBA from Alfred University. Welcome, Devin. It's over to you.
Thank you so much, Rihanna, for the introduction. I appreciate it. And, of course, thank you all for joining us for this webinar today. And thank you for those who would be listening to this recorded session. That's also appreciated. I'm going to jump right into the agenda in just a second. I want to first take just a real quick minute to highlight the reason I'm going over this particular webinar. So we all have, good intentions with safety, right? You're on this webinar because you care about machine safety in some form or fashion. And when I do see machine safety being implemented in the field, again, there's good intentions there, but I also unfortunately do see at times where we don't take that extra step to make sure that control measures, the safety functions, whatever we're adding to this machine to make it safe, that we don't take those extra steps sometimes. And so the control measure that we're trying to implement may not be actually safe. Okay, so I want to take this time to highlight the reason behind this webinar. And in order for me to focus on what do we do to take those extra steps to make sure that we are applying these engineering safety control measures to make that safer workplace, we're going to look at this agenda here, where we're going to start off by looking at the hierarchy of risk control measures, and I'll go over what that is. But that will then lead us into safety design considerations for fixed guarding, as well as safety design considerations for movable guards. And when we get into those, I'll start to introduce some safety standards, see what's out there, what we need to focus on to make sure we're taking that extra step, right, to complement our good intentions for our safety control measures, make sure that we're implementing them correctly. We'll then look at presence sensing devices, and I'll explain how they fit in, why they're in a separate section. Again, looking at some safety standards that we want to keep in mind. And then, as Rihanna mentioned, we'll have some time for Q&A. Right? So please feel free to use that question field as I go over the content that I prepared for you. If you have any questions, We'll get to them either live now if there's time for all the questions. If not, I'll do my best to get back to you in a timely manner to answer your questions, in email. Okay, but please, by all means, use that question field so we can capture and answer those questions for you. Okay. With that, let's go ahead and jump into the presentation here. Okay, so everything that I'm going to go over for implementing engineering control measures, this is all based off one important element, and that is a risk assessment has been completed. Okay, so we're kind of jumping a step here and saying that a risk assessment on this machine has been done. We've had, previous webinars where we went over the entire process of a risk assessment. So I definitely encourage you to take a look at some of those webinars. And if you remember, if you were part of those webinars, or even if you just know about the process of a risk assessment, you may recall that a risk analysis is, one of the first parts of the risk assessment. The risk analysis is where you are evaluating the machine, like determining the limits of the machine, who used this machine, what are their tasks, and you are identifying the hazards and risks associated with this machine. Right? So you are analyzing the risk associated with the equipment. Okay. Once that's done, once you identify the hazards and risks on the machine, the next steps within the risk assessment process is trying to reduce the risk that you have identified. Okay, so we get into this idea of risk reduction, and then that brings in the hierarchy of control measures, which you may have seen in some of your internal safety trainings at sometime in some form or fashion. But I'll go over it here again, right? The hierarchy of control measures. So when you find a risk for a machine, whether it's a brand new machine that you're designing, if you're an OEM, or if it's a legacy machine, if you're an end user, or if you're an end user having that conversation with an OEM for a brand new machine, you identify the hazards and you want to see if you can design it out. Right? Let's see if we can eliminate the hazard that you have just identified. If you cannot eliminate it, then we say, okay, well, can we at least substitute it? Like, can we substitute this dangerous hazard for something that's a little less dangerous? If we can't substitute it, or if we need to take further action, we'll then say, okay, let's look at engineering controls, which is the main focus on this webinar. So as you can imagine, we'll spend a lot of time on this section here, but this is the next step, right? If we can eliminate and substitute, let's provide some engineering controls so that we can reduce the risks for personnel to these hazards. Okay. If further action is still needed, we can then look into administrative controls, and then finally PPE, like personal protection equipment. What you may see typically is a combination of more than one of these, right? So if you are trying to safeguard a machine and you say, you know what, let's add on some light curtains, right, or a guard or interlock, you are essentially creating a safety function. You are adding engineering controls to this machine for safety. You may then say, you know what, we also need some additional administrative controls, right? Maybe we need some additional trainings, and maybe this area needs to be controlled access, so we have administrative controls, even though we have engineering controls. And then also PPE, right? This is an industrial environment. We want to make sure that we're providing proper PPE for personnel as they interact with this equipment, whether that's hearing protection, eye protection, cut resistant gloves, whatever the case may be. But you usually see a combination of these. And as you go from elimination down to PPE, we look at what's most effective, which is eliminating the hazard, down to what's least effective, which is just relying on PPE. Okay, but again, the focus of this webinar is engineering controls. So let's go ahead and let's dive into that section of engineering controls. Okay, so when you look at engineering controls, we can there's two main categories, right, where we look at separating guarding and non-separating guarding. And separating guarding is providing a physical barrier between us and the hazard. Right, that's separating guarding, separating us from the hazard. And then there's non-separating guarding, where there is no physical barrier. And for non-separating guarding, we're looking at those presence sensing devices, which, as you see on our agenda tracker on the left, is right before our Q&A session. So we'll dive into that as well. But for separating guarding, where there's that physical barrier between us and the hazard, we can have fixed guarding and or movable guarding. And we'll look at the definition of these two, and we'll bring in some standards in just a second, right? But it is what it says, right? Fixed guarding is a fixed structure, right? That's protecting us from the hazard, or at least separating us from the hazard, right? If it's protecting us is a different question, which is the purpose behind this webinar, right? A movable guard is a guard that can move, right? So that we know what that is, but let's look at the actual definition from a standard. So we'll introduce one of many standards that we will look into today. This first one being ISO 14120. The actual title of the standard is General Requirements for the Designs and Construction of Fixed and Movable Guards. So exactly what we're looking at. The latest edition is, I believe, edition 2, 2015. I know it was reviewed and confirmed in 2021. So if you have edition 2, 2015, that's the latest version of ISO 14120. But here they give us the definition of a fixed guard. And I also highlighted in blue some key terms from the definition. Right? So a fixed guard is a guard is fixed in such a manner that it can only be opened or removed by the use of tools. Okay, and the use of tools, I'll explain in, I think, the next two slides. That's the next slide. I'll explain what we mean by the use of a tool. Okay, the purpose behind a fixed guard is to prevent or reduce access to the data zone, right? Reduce exposure. Going back to our previous slide, we have a risk. We're trying to reduce exposure to the risk. We see by definition from ISO 14120, fixed guard's purpose is to reduce access to the hazard, right? Reduce exposure, right? So we see how this aligns right off the bat. Okay. Now, the thing with everything that we're looking at, going back to my highlight of why we're doing this webinar, right? Good intentions, right? We see that there's a hazard on the machine. We want to guard it, so we say, yes, let's go ahead and put some hard guards around this equipment. Good intentions, but do we take the extra steps to make sure that we are applying it correctly? Okay, so now the question is, what are some of those quote-unquote extra steps? Okay, so some things we must consider when we are trying to apply guarding, hard guarding, fixed guarding here. Okay, the first thing is ergonomic attributes. Okay, so anytime we add on a control measure, whether it's hard guards or whatever we look at later on, we want to make sure that we are not introducing an additional hazard. Okay, and I have seen, and on the floor, right? I've seen it before where, again, good intentions. Let's add on some guarding, and let's add on some hard guards to protect against this hazard. And I've seen where the hard guard itself has created an additional hazard. I've seen situations where the hard guard now creates an impact hazard to the operator's head. So every time they interact with this machine, they actually were hitting their head on this newly installed fixed guarding. Okay, or again, ergonomic attributes. Now we have guarding. How does the operator interact with the equipment now? Right now, if they have to load equipment or load a part to the machine, do they have to, maneuver around this fixed guarding and contort their body? Now we're adding an ergonomic hazard. So we have to look at how personnel are using the machine before we start to apply these fixed guardings to the equipment. When we look at assessments, A lot of time and resources are spent on making sure that the operator is safe. Okay, yes, the operator has the most exposure to the machine, I would say, right? They use the machine day in, day out. They have the most exposure. But the maintenance personnel, for example, will probably have the most dangerous exposure because they're doing tasks what's called upon them to maybe remove or even bypass a guard while the machine is running, right? To do maybe some type of troubleshooting or setup. So we also must consider other personnel other than the operator. Right? We have to look at who uses the machine, everybody that uses the machine. But we bring this up because we have to consider things like lubrication points. Right? So if the OEM manufactures this machine and they provided easy access points for maintenance to provide lubrication to the equipment, and now we've done an assessment, identified some hazards, let's say for the operator, and we install some fixed guardings, and oh man, now we've blocked off these areas for maintenance personnel, and now when they have to do what was before a 5-minute task to provide lubrication, now they have to go into a full-blown lockout tagout procedure because they're removing hard guards, right? So we have to take that into consideration as well. I don't know if you can see this picture clearly, but here we show a fixed guard, and we have it circled, so it's highlighted of the fixed guard that is essentially damaged. So this guard received an impact from inside the hazardous area, and it did not break, right? But it definitely was damaged, and we have to look at what are we guarding against. So if we have an area where there's potential for product to be ejected from the machine, so we have flying projectile, okay, we want to make sure that the guard can withstand the impact of the product, right? So maybe the system is designed to project a part into a bin, but let's say it doesn't hit the bin; it actually hits the guarding. Well, we want to make sure that that product doesn't break through the guard and hit an operator at an operator station, or hit somebody walking through a walkway. We can also take this same concept and look at a robot, right? And we say, okay, well, if we maybe have an old robot or a non-safe robot where we don't have safe stops, soft stops, or hard stops, well, maybe we don't have enough room either to expand the guarding to protect against a runaway condition with the robot. So we have to have the guard close by. Again, in this rare instance where we don't have soft or hard stops, maybe we have a guarding that can withstand the impact of a robot. So if we do experience a runaway condition, the robot will smack into the guarding. The guarding will maintain itself, right? It won't go crashing through and hit an operator or personnel walking by. As you can imagine, though, if it can withstand the impact of a robot, that robot's probably going to be damaged. So it's probably not the ideal solution. We probably want to look at soft stops or hard stops at a minimum. But again, we're looking at things we want to consider. So let's look at what we're guarding against to make sure we have the right material for that guard. Visibility. So if you can see this on the screen here, we have an example of yellow mesh and black mesh, and those are the two main colors for mesh when we look at safety. And a lot of people tend to gravitate toward yellow because yellow signifies safety. But if we look at this comparison between the black mesh and the yellow mesh, we see that it's easier to see past the black mesh to see the boxes, right? Yes, you can see the boxes behind the yellow mesh, but it's easier to see it behind the black mesh. And that's because the black mesh is absorbing the light, so we can see past it to the boxes. This is to compare it to a machine, right? So if we were guarding a machine and we want to give operators or technicians or maintenance personnel the chance to view the machine easily, let's consider using black mesh if we're using mesh at all. Okay, So this is just a real quick example between black and yellow mesh, but imagine an entire cell, an entire industrial plant floor filled with yellow mesh, okay, and how hard that would be to focus in on this one section of the machine when you're trying to just see what's going on, okay? If we can provide easy visibility, this would reduce the chances of bypassing, reduce the chances of us having to interrupt the process by opening up a guard door to see what's going on. So it's something to consider. Okay, of course you can use, if the application allows, you can use Lexan. Then you also want to make sure that there's no heavy glare with overlights, but again, all things that you want to consider. When we look at the definition of fixed guarding, part of that definition said that we have to use tools to remove the guard. That's the definition. That's called out in the standard. The type of fasteners that you can use depends on, honestly, the operator task. Okay, so the thing behind this is that we have to use fasteners that require a special tool for removal, and that definition of a special tool for removal will be dependent on the site. Even if it's different sites within the same company. And that's because when we look at what they mean by that, as far as the definition, we mean that the operator, okay, if the operator has certain tasks that are assigned to them that requires them to use a tool or, let's say, adjustments, we cannot use fasteners for the guarding that tool can be used to remove. Okay, so we have to use other types of fasteners. General rule of thumb, right? Easy fasteners to fall back toward security type fasteners, one-way screws, things of that nature. Again, we're concerned about the operator. In this case, as far as the special tool for removal, maintenance will always have the tool for removal, right? It's part of their job in order to remove guarding, whether it's for rehaul the machine, preventative maintenance, troubleshooting, whatever the case may be. There's no special tool for the maintenance personnel, right? We're looking at operators here for this definition. Okay. So again, we're looking at fixed guarding. So these are some things we need to consider for fixed guarding. All right. Going back to my original statement, like good intentions. Yes, let's put on a guard, but let's take the extra steps. Let's take these considerations in mind. Another standard focused on fixed guarding is ISO 13857. Here I have the definition listed on the slide, but we are focused on the safety distances to prevent hazard zones from being reached by upper and lower limbs. So inside of this standard will be tables to help guide us on where to place these hard guards. All right, so it'll, for example, give us a table for the mesh opening, and it will ask us, what's the shape of the opening, what's the size of the shape of that opening. And based off of these parameters, it will tell us what is the minimum distance we have to place this guard so that we can easily, reach our finger or hand through and reach the hazard. Right? Take those extra steps to make sure that we are applying this guard at the right distance. If we can reach around the guard, it takes into account, well, let's limit the motion of the arm or the forearm or the hand so that we can reach the actual hazard. Okay. It also has this table inside of the standard where it looks at what is the height of the hazard, what is the height of the guard, and this will allow us to determine where we can place this guard, what's the minimum distance. And if we just think about what this standard and what this table in particular is trying to tell us, it's the closer we are to the hazard, the higher the guard has to be. And we know that, right? The closer you are to the hazard, the higher it has to be, so we can't easily reach over. And the further you are away from the hazard, the lower the guard can be, as long as we can, just easily step over it. So that right? That makes sense to us. But here it is laid out in the standard that we can easily reference, document. Okay, so again, taking those extra steps. If we go into movable guarding, We'll introduce another standard here, ISO 14120. All right, because when we look at movable guards, we're looking at a deliberate action to open up a guard. And we see in this definition within ISO 14120, we see some shall statements in there. So shall require a deliberate action. A movable guard can be on a hinge guard, or hinge doors, a slide-in door, counterbalance, a full lift-off door. But whatever we're looking at, it moves. Okay, we can move it, and we can gain access to this equipment. That's what a movable guard is. The purpose, again, going back to the original slide about the risk assessment and risk reduction, the movable guard purpose is to prevent or reduce access to a danger zone, right? Reduce exposure to the hazards. The thing with the movable guard is it can move, and it will allow us to get access to the machine. Because of that, we can move this guard, we now look into another standard, ISO 14119. Okay, so I'm throwing out a lot of different ISO standards at you. ISO 14119 is another safety standard that looks at the interlocking devices associated with guards. In particular, it looks at the principles for design and the selection of interlocks for these guards. So this brings in the discussion of interlocks, okay? And we have here on the slide a statement from ISO 14119 that says movable guards shall, and shall should probably be highlighted in blue also, that's important, shall be associated with an interlock or an interlock with guard locking. What is that? What do we mean by that, right? So when we open up this movable guard, the system must know that the guard door is open. So we have to send a signal to our system to trigger a safe stop, a safe condition. And that's an interlock device. Right? We put the machine into an interlock state. Interlock with guard locking is a step further where we are actually locking the door until we reach a safe state. Okay, good intentions, right? We have a guard door that can open. We want to go ahead and put on a safety device on there. Well, if we open up this guard door, is there going to be residual motions that will allow us to be exposed to a hazard? If there's going to be residual motion, so it takes a couple of seconds for the machine to come into a safe state, that triggers us to look into a guard locking device. We need to make sure the guard remains closed and locked until we reach a safe state. Okay, an interlock device, we open up the guard door, and essentially the machine comes to a safe state instantaneously. There's a difference between those two. Let's take it a step further, and let's dig a little deeper into this as far as the interlock devices go. Okay, so we know that a movable guard shall have a interlock device. Depending on the application, we may have to also incorporate a locking function with this interlock. Okay, what are we looking for our basic requirements for a safety device? Because you can do a Google search, right? You can try to find an interlock device, and there's plenty of options out there. What are we looking for? What makes this a safety device? So for interlocks, there are two main principles, right? There are a couple of options out there for operating principles, but for the sake of in our webinar, right, we'll focus on two, right? So there's the option in the industry for electrical mechanical devices, which are what I would call simple, quote unquote, simple devices, right? Where we have in most cases, like a key on a door, a switch on a frame. You close the guard door, the key gets inserted into the switch, some cams rotate, and some contacts close. And that closed contact will signal that the guard door is closed. An electrical mechanical device. Same concept for a limit switch with contacts, electrical mechanical contacts inside. Hinge switches, trap key systems, and also electrical mechanical locking devices. right? Where again we insert the key into the switch, but now the key is locked into place until we receive a safe signal from the machine. Okay. On this screen here, I show a circled arrow representing a normally closed positive break contact. I will explain that in the next slide. Okay, I'll highlight that and I'll come back here. But of course, please use the question field if you have any questions as I go over the positive break contact. In addition to electromechanical, another common operating principle for an interlock in the industry is some form of electronic devices, where the electromechanical are normally open, normally closed contacts. Electronic devices typically, right, because there's always exceptions to the rule, there are different options in the industry, but typically what you're getting from an electronic device is a PNP semiconductor 24-volt output, similar to that from a light curtain or a laser scanner. These electronic devices, I call electromechanical devices, quote unquote, simple devices. Electronic devices are more high tech, right? They have built-in diagnostics, built-in monitoring typically, right? They have the LEDs on there. You can see the status of a switch when it's open and closed. Some manufacturers have more information based off the LEDs, right? But both of these technologies, electromechanical or electronic, can be used in the highest safety circuit allowable, right? Performance level E, category 4. Right? Even the quote-unquote simple limit switch has a place within safety, right, for different applications. A step further, right? I want to keep going a step further. Right? So it's one thing to say, you know what? Yes, let's add on a safety device because we know we need a interlock on this movable guard. Then the thing is, okay, well, let's make sure it's safety rated, right? Let's look at the operating instructions, make sure that we see, those IEC standards, UL, TUV, CSA, all the requirements to check the box. Perfect. Let's take a step further, though, because this still doesn't mean we have a safe application. We're not making it a safer workplace. Let's dive deeper for these control measures. So let's take a step further. To take a step further, I want to go over this example with you. All right, and what we see inside of this gray box, on the left side, within this gray box, we see a guard door in a closed state. Okay, while this guard door is closed, we see that a limit switch is being activated. Inside of that limit switch, we see a closed contact. So the guard door is closed, limit switch is activated, contact is closed. We are sending a signal to the machine that the guard door is closed, the machine can run. Perfect, right? On the right side of this box, when we open up the guard door, we no longer are triggering the limit switch. That contact we see now was open. This open contact drops out our safety, the machine stops. Okay, so 10,000-foot view, this is exactly what we want. Guard door closed, machine runs. Guard door open, machine stops. Okay? I say 10,000-foot view because we're drilling down, all right? We're digging deeper. So let's dig deeper. If we look closer at what's going on, we will see that this is actually incorrect. This is not what we want as far as this operating principle. What we have here is something that's called negative mode mounting. Okay, and what we can see here is that this switch would, or could, I should say, could fail in an unsafe state and can easily be bypassed. Okay, so the bypass portion of it. This is a recorded webinar. Okay, so I am not saying to do this, but if you go to a machine and you look up on a machine and you open up the guard door and you can pinpoint a limit switch, you can physically see the limit switch. All right, and if you were to push down on that limit switch, you may see the HMI say, "Oh, guard door is closed." Well, the guard door is physically open. That's not right. Okay, so we can easily bypass that switch. That is something that we do not want in safety, obviously. Okay. The other thing is that it can fail in an unsafe state. Right? So in this picture here, while the guard door is closed, let's introduce a stuck or welded contact. So when we open up that guard door, that contact remains closed. Machine continues to run. Okay, so you may have a situation where you have an environment where the safety culture is top notch, right? And you say, well, no one here is going to bypass a device. And that's not part of the safety culture here. One strike and you're done. Nobody does it. That is perfect. Right? That is the great environment that we want everybody to be in as far as a safer workplace. But now what about the fact that this can fail in an unsafe condition? Okay? Because again, when we look at this failure, when we open up that guard door, that machine is running in this situation, running at full operational speeds. Okay? Again, something that we don't want to do. We don't want to happen. So how can we utilize a limit switch in a proper safety circuit? Okay, well, we want to implement what's called positive mode mounting with the use of a normally closed positive break contact, that circled arrow that I mentioned in the previous slide. So what is different here? Now with the guard door being closed, the limit switch has that closed contact internally. Can we bypass this switch? I mean, we can force the plunger down, but if we force the plunger down, we're going to open up the contact and we're going to stop the machine. We're not gaining anything by bypassing this limit switch. Can we remove the limit switch? Yeah, sure. Right, you can remove it. That goes back to ISO 14119 and 14120 to make sure that we're using tamper-proof screws on that limit switch. Right? The goal is to make it difficult to defeat. Okay. The other thing is, if there's a failure, a welded contact, when we open up that guard door, we now see in this image that we are forcing the plunger down. We're going to rip open that contact. Right? That's a safety contact. We're going to rip it open, even if there's a failure to maintain safety. Okay. Now, I see negative mode mounting consistently on legacy machines and unfortunately on brand new machines being designed today. Okay, so we now have an understanding of what that is and why that is not appropriate for a safety circuit. Okay. Again, please use the question field if you have any questions based off of that. Right, this can be a webinar in itself, probably, honestly. But okay, so now we need to check some boxes, right? The hard guard, the fixed guard, is at the right height, the right distance, okay, based off of our standards, ISO 13857 and ISO 14120. For our movable guards, are we using a safety-rated interlock device? Okay, are we mounting it correctly? In this situation, negative mode or positive mode mounting. Let's go one more step further, right? Because you can spend the money on the top-notch devices, okay, and mount them correctly by following the mounting and wiring instructions. But is it wired correctly? So here's a whole nother discussion, and this brings in another ISO standard, ISO 13849, which looks at the safety-related parts of the control system. Okay, there's two parts. The first part is for general design principles. The second part is for validation of that safety circuit. So what you're looking at here for this particular standard is, let's look at the hazard that we're trying to guard against. We already know that we want to add on in this case, an interlock device that is a safety function. So this standard will say, okay, well, let's look at the hazard that you're trying to guard against. Let's look at the severity of injury of this hazard. Let's look at how frequently you are exposed to this hazard. And let's look at the possibility of avoiding the hazard if you are exposed to it. And this will lead us to a performance level requirement, PLR. And there's a performance level A, B, C, D, or E. And then there's plenty of different parameters that go into what a performance level is. Part of that is how the switch is physically wired up for the safety circuit. Is it a dual channel? Is it a single channel? Is it going to a safety monitoring device? Is it going just to contactors? Are the contactors being monitored? Right. So there's a lot of different parameters for a performance level, but one of them is how we are physically wiring up the safety circuit. Okay. Again, I believe, no, I know we have a webinar on this topic as well. Highly encourage you to look at that. This standard ISO 13449, I've seen, full one-day seminars on this or trainings on this. I've seen, 4-day trainings on this. It can get really deep because it does involve a lot of calculations for a performance level. But again, we want to make sure that we are implementing these control measures correctly. And so based off of the risk assessment, right, what do we define as the hazard, or what do we identify as the hazard and the risk? Right? What are going to be our control measures, our engineering control measures, locking device, not locking device, so forth and so on. And now it's how are we going to wire that circuit, that circuit to make sure that we are protected in the event of a dangerous failure of our safety function. To help understand this portion of it a little better, right? This idea of dangerous failures and performance levels. Let's take a situation where we have a hazard that can cause an amputation or a fatality. Okay, you go through your risk assessment. That should be, depending on how often you are exposed to the hazard, of course. But usually, there may be a high hazard for this machine that we need to guard ASAP, like maybe high on the list. We then say, okay, we're going to add some hard guards, right, based off this hazard, and some movable guards. Maybe we need access to this area, so we add some movable guards, and we'll add an interlock device on there. And then this standard kicks in, okay? And we need to look at how reliable our safety circuit is. And if we look at, a single device, single safety device, interlock device, with that has two channels, we may experience a failure on one of those channels. Okay, if I or you were to go to this machine that has been identified as having an amputation or fatality hazard, and we open up this guard door, and this safety function experiences a failure, like you, right, I want to make sure that this machine still comes to a safe state, even though there's a single failure, right? And that's where this standard kicks in, right? Depending on the hazard that we're trying to guard against, we need to look at what are some of those dangerous failures and how can we make a safety circuit to, possibly be resistant against at least a single failure. Depending on the hazard that we're trying to guard against, there may be a situation where the safety circuit needs to be resistant against multiple failures for that performance level E category 4 type of. Again, a lot behind this. This could be its own webinar, which it is, which we we do have a webinar on this. Again, definitely encourage you to view that. In addition, 14119, which I mentioned earlier, the standard for the standard for interlock devices associated with guards, also takes into account preventing bypassing. And again, if you have the site where nobody's bypassing safety in here, perfect. Maybe you don't have that culture that you're trying to aim to, or maybe you're an OEM that's trying to design a machine that's not easily bypassable. Okay, so ISO 14119 does give some guidance on how to install these interlock devices to help prevent bypassing. There's actually a mini risk assessment or a flow chart inside of ISO 14119 to help you understand, is there a high possibility for bypassing? Okay, and if there is, they lead you to this chart as an option to help prevent the bypassing. And what this chart is showing is that it's It's listing the different types of interlocks, and based off of the type of interlock is giving you some requirements and some recommendations on how to mount that device. Okay, so again, there's a lot of information within the standard. If I can try to summarize it, the standard calls out different types of interlocks, whether it's mechanical, uncoated, non-contact uncoated, or a trap key system, which is its own type now with this new standard that has just been revised. And then looks at, as far as it being coded, what are is it a low, medium, or high coding for this device? If it's a high coding for the actuator for this device, there's less requirements that you have to do, because for a high coded device, it means that there are over 1,000 different options for an actuator. Okay, so it's quite difficult for someone to go to a tool bin to pull a spare actuator from the device for the device and bypass it. So if you have a high coding device, honestly the main requirement is to attach that actuator, that golden ticket for bypassing, attach it to the door with tamper-proof screws. That way we can't easily remove it and bypass the device. For situations where we're not using a uniquely coded actuator, some of the requirements may be installed in the device where we can't easily reach it, so concealed within the machine, things like that. So it's a nice table that we can use, whether we are trying to implement safety on the legacy equipment, or again, if you're an OEM trying to design equipment, let's see what we can do to help prevent bypassing of these safety devices that we're trying to implement. We have good intentions. Let's take it a step further to make sure that we're implementing correctly for our best safe practices. I mentioned earlier, right, there's separating guarding, physical barriers between us and hazards, and then there's non-separating guarding. So now we're looking at this idea of non-separating guarding. And as I have it listed here on the slide, right, these devices or these types of guarding does not provide a physical barrier between us and the hazard. Right? There is absolutely nothing that is preventing us from reaching past or walking through, a light curtain. Nothing preventing us from actuating a two-hand control or stepping through a scanner or on a mat. Okay, because there's no physical barrier, we need to make sure that the devices are installed at the appropriate distance. Similar to the hard guards, right? Yes, we want to use hard guards. Let's make sure that the right distance. Yes, we want to use light curtains. Good intentions, right? Yes, we want to use scanners and safety mats. We want to make this machine safe. But let's dig deeper, right? So in order to dig deeper, to make sure that we're implementing this correctly, we'll look at one more standard before we head to the Q&A. Again, we have another webinar. So we've done quite a bit of webinars. Right? So we have another webinar on the safe minimum distances, which, again, I encourage you to review. So this is something that we did highlight in one of those webinars, but I want to bring it here again because this is something that is constantly overlooked. Right? We want to use these light curtains and safety mats and scanners. Perfect. Right? Let's go ahead and implement these safety control measures, but let's implement them. Let's implement them correctly. Right? So here is a incorrect implementation. Right? So here we have machine running. We'll see that at the entry we have a set of light curtains. Right? So we have somebody that's going to walk through the light curtains into the hazardous area, but we have a stop signal. The machine is slowing down, but it's not stopped. And unfortunately, we are fully exposed to these residual hazards. Okay? Again, I've seen this before, unfortunately. I haven't seen an accident, but I've seen situations where light curtains were not installed correctly and machines will continue to run if we were to continue to reach in or walk into this area. Okay, so our last standard for the day, ISO 13855. This standard looks at the correct positioning of safeguards with respect to the approach of the human body. Okay, so the appropriate distance for, in this case, a light curtain. This standard has, you know, pages and pages and pages of formulas to help us understand where we need to place these light curtains, where we need to place these scanners and safety match to and controls. There's a formula in there that we have to use to calculate the safe minimum distance. But the first thing is being able to calculate stop time analysis. Okay, so we have to go through a scientific measurement of seeing how long it takes this machine to stop. We then take that stop time measurement into the ISO 13855 calculations to be able to determine the safe minimum distance. Okay, so the intentions. Let's add these light curtains. Perfect. Let's take it a step further. Let's do the scientific calculations so that we know how long it takes this machine to stop, and let's place these light curtains at the right distance. So here on the screen we see the faded light curtains that were at the incorrect distance. We now see the light curtains pushed back a little bit. Now we can walk through. We'll send that stop signal, and by the time we get to the hazardous point, we have a safe condition for the machine. Okay, and yes, this is a little exaggerated, right? But it's something that we need to focus on. Okay. Perfect. Quick summary, and we'll have some time for some questions, and I think some questions have come in. So quick summary here, right? And again, we touched on a lot of different topics, right? But that was the purpose of this webinar. Let's look at all these individual topics, and then again, some of these we can spend a whole day on. We have individual webinars that goes into way more detail with some of these topics. But the main thing is to hopefully was to help you understand that we have to dig a little deeper with these good intentions to make sure that we're implementing safety control measures appropriately. Okay, so real quick summary. Again, everything that we showed, right, it starts off with the risk assessment or a risk analysis, so we understand what we need to guard against. Okay, the engineering controls can be a combination of fixed and or movable guards. We looked at quite a few different standards, right? ISO 14120 provides us guidance for the structure of the fixed guards. We want to make sure that as we implement these fixed guards, we want to take into account the ergonomic visibility, the fasteners for these guards, in addition to the fasteners for the devices, right? ISO 13857 helps us understand where we can place these guards, right? How high the guard can be, how far or how close the guard can be based off of the openings of the mesh, for example. ISO 14119 looks into the devices or the interlocks for the movable guards. Helps us design a safe solution to help prevent bypassing. Okay, ISO 13449 is for the performance level, how we are actually designing and implementing these safety circuits. And then finally, ISO 13855 for the safe distance for these present sensing devices. Okay. So we have a little over about 5 minutes. So I will bring Rihanna back on to see if there are any questions that came in.
Yes, Devin, thank you so much. That was really robust. Your presentations are always so packed with information, and we do have quite a list of questions that we'd like to get through, and we'll barrel through them. But just as a reminder, if you would still like to submit a question, type your question into the question window on the side of your screen and hit the submit button, and Devin will get back to you for those questions that we possibly will not get to today. Also, please stay until the end of the presentation to complete the exit survey, which will pop up on your screen. You can preview the questions now by clicking the exit survey icon on the left side rail. Okay, Devin, let's go. Here's the first question. What place does acceptable risk have in the risk assessment and guarding? How would you approach a customer pushing back on guarding if they have a higher tolerance of risk?
Okay, so there's nothing honestly in the standards that really define an acceptable level of risk. There's nothing in any standards that say the risk has to be reduced by a certain percentage or to a certain number. The key thing that we want to focus on that when that kind of conversation, honestly, it's foreseeable, reasonable, foreseeable, acceptable levels of risk, and that's definitely a conversation. And the end users, they have a heightened responsibility, right? When we look at the OSHA requirement, it is up to the employer to make a safe working environment. So sometimes they have a heightened level, a heightened requirement for safety, but it does come down to that reasonable, foreseeable, which again it is subjective. I'm not gonna lie to you, right? It's subjective. But if we can bring it back to that concept, reasonable, foreseeable, what can happen? Here are the documented hazards that you've identified as an OEM. Here are the control measures that you put in place as an OEM. Here's the after ranking of the hazard. So as long as you can provide documentation that you've taken your due diligence as an OEM, that would help. And I promise you, I promise, this is not a shameless plug. But if some customers do say, you know what, bring in a third party consultancy to confirm it, sometimes that does help the conversation if it needs to go that far. So hopefully that helps a little bit with that question.
All right, thank you. So here's one more. You mentioned that maintenance will have any tool to remove any component of the system, and fixed guards should be mounted with fasteners an operator will not have access to in their job. So assuming an operator has access to no tools, what advantage do tamper-proof screws offer? Are tamper-proof screws required on fixed and movable guards as well as on presence sensing devices? And finally, what type of hardware should be used on removable guarding, such as an access panel?
Well, okay, let me see if I can get all those questions.
Yeah.
Okay. All right. So, and please use the question field if I didn't answer the questions in full. But let me see if I can answer you. So, as far as the operators, so if the operators do not have any tools, you have way more options for those fasteners. No, they don't have to be, one-way screws, especially if the operators do not have access to them. If the operators do not have any tools. I just refer to, one-way tools, tamper-resistant tools as a general rule of thumb to fall back to. But no, that is not a requirement, especially if the operators do not have any tools. For fixed guarding, again, we just say that, or not we, but the standard says that you have to have a tool to remove it, right? And again, if you say the operators do not have any tools that they can use to remove it, then we at least have to say, okay, well, we're not using thumb screws, right? Because you don't need a special tool for thumb screws, wing nuts, things like that, right? So things that we can essentially, honestly, use your hand, and yeah, it may be torqued pretty good where you can argue that you can't use your hand, but at the end of the day, you're not using the special tool, right? So things like that will be considered inadequate. And I think there was one more part of that question. Was that part of our interlock?
Yeah. Sorry, Devin, are you querying? Okay, so what type of hardware should be used on removable guarding, such as an access panel?
Same thing. So you still need again tools, fasteners that operators do not have access to. Honestly, there may be situations though, right? So if we have fasteners on there, we also may need to consider possibly, right, if it's something that we are removing quite frequently, maybe an additional interlock on there so that we know that the guard is back in place. So it's something to consider. But Again, you don't necessarily need more special type of fasteners if the operator does not have access to. But please, again, I can look at that question again and send an email. I just want to make sure that was quite a few different parts to it, and I know we're at the 3 o'clock mark, right, or the hour
Yeah,
mark, I should say.
it's a good one for sure. So here's one more. As technology advances, are you seeing more interlock guarding, light curtains, perimeter gate accessing guarding, or is it a combination of all?
Honestly, it's still a combination of all, right? So yes, we were seeing more, applications with, the electron devices as customers and OEMs get more familiar with some of these newer standards with performance levels and still ratings. It's easier to get to those higher still ratings, performance level using, the electronic devices. But still, you still have a ton of legacy equipment in the field where if you're doing upgrades and modifications, it's still easier to use, those, I'll say legacy electrical mechanical devices. So honestly, at the end of the day, there's still a combination of both. But I would say for newer applications, for newer machines, as customers and the OEMs try to meet, ISO 13459, for example, yeah, there's definitely an uptick on those electronic devices.
Hmm. Okay, here's one more. ISO 14119 was referenced as being a newer standard. Were there any major changes with this latest revision?
Yes, so there was quite a bit of change, honestly, for the standard. We look at as standards get revised, and most cases, a standard gets looked at, and they say, "Yep, it's still good," right? This one was really revised, and as far as some terminology, to me, two of the big things probably that were modified with ISO 14119 is they introduced a new type or a new category for device, which is the trap key systems. That's now a Type 4. I'm sorry, a Type 5. But more importantly, I think, is they went into incredible detail for the concept of fault masking and what that does to the diagnostic coverage for the safety function. I mean, there's and the whole annex for it with a bunch of different examples. Again, we spoke about fault masking before in some of our webinars. We made white papers about fault masking, but this standard might be one of the first standards that I've seen that goes into this much detail, trying to help you understand what that is and how to avoid fault masking.
Devin, we have come to the top of the hour, and I just want to say I'm so thankful for all of the questions. Thank you very much. For those questions that we were not able to answer, we certainly will get back to you. So now that we're out of time, it concludes our presentation today. On behalf of Machine Design, EHS Today, and NED and Endeavor Business Media, thank you very much for attending. I'd like to thank Devin Murray for a great presentation and Schmersel for sponsoring today's event, and of course all of you for joining. And finally, don't forget to take the exit survey that will pop up on your screen at the end of this webinar. Have a great rest of your day.